This is dark, and it has huge mass, and it's small. That's 3 smoking guns right there.
Right.
Implicating a supermassive black hole.
The cosmos far beyond our planet is filled with things so weird and wonderful that it can be difficult to believe they exist. But is there anything stranger in the universe than black holes? These bizarre, gravitational monstrosities don't only warp space and time. Just thinking about them stretches and bends people's imaginations as well. We don't yet know all the details of how black holes work, but this is not the same as having no knowledge at all. When James Webb Space Telescope opens its eyes on the universe, it sheds light on some mysteries hidden inside the gluttonous beasts. The $10 billion time machine has captured a bunch of images about black holes. These findings reveal the never-before-seen details of the supermassive black hole that defied our understanding, one of which even exposed the astonishing truth about the expansion capabilities of black holes, uncovering their true scale. Join us as we dig deep into the shocking discoveries that left scientists astounded. Black holes are one of nature's strangest creatures. They push the laws of physics to their limits, and at their center, those laws go belly up like a bug dosed with Raid. A black hole will form anytime a lot of matter gets jammed into a small space. This can happen when massive stars reach the end of their lives. Stars contain a lot of mass, which means they produce a lot of inward gravitational pull. Stars usually support themselves against their own weight by producing energy at their centers via nuclear fusion. The energy pushes outward, balancing their gravity, but when a star's fusion fuel runs out, the crush of gravity wins. For massive stars with many tens of times the mass of the Sun, no force can hold off the gravitational crush. All the matter in the star falls inward and gets squeezed down into a single geometric point. That is when a black hole is born. What makes black holes weird and causes them to push physics to the edge is what they do to space and time. Einstein, with his general theory of relativity, was the first to recognize that gravity is not a force, but actually a stretching of the fabric of space-time. After Einstein, we could no longer think of space as an empty stage on which the drama of physics plays out. Instead, space and time are the components of a single entity called space-time. This entity is a kind of thing that will stretch and bend depending on how much mass energy is around. Yes, mass and energy are also no longer separate. All matter distorts the space-time around it, creating a kind of well. Other mass, feeling the stretched space-time, will fall into the well. Black holes take this phenomenon to the extreme. When the matter at the center of a black hole gets squeezed into that single point, it forms what physicists call a singularity. Basically, the density becomes infinite and the stretching of space-time becomes infinite too. General relativity breaks down at the singularity, and no one knows what happens there. But general relativity also tells us that an event horizon forms around the singularity. This is a surface of no return. Anything that crosses the event horizon, even light, is forever cut off from the rest of the universe as it heads towards the singularity. Scientists have talked about black holes for nearly a century, but we have only recently been able to observe them, and even then indirectly, by looking at light that comes from the material swirling around the black hole's event horizon. We simply have not had the technical capabilities to capture a direct image of an event horizon and see exactly what is happening at the point of no return. That is because black holes are really small. The Sun has too little mass to ever become a black hole, but if it did, its event horizon would be just a mile or so across. That means stellar mass-sized black holes at typical stellar distances are too small to see, even with the best telescopes. Luckily, black holes come in another flavor. At the center of most galaxies, matter gets funneled inward, creating what are called supermassive black holes. These things are monsters. They can be billions of times more massive than the Sun. That means their event horizons are also billions of times bigger. In 2017, astronomers linked a bunch of radio dishes across the planet to create an Earth-sized telescope. Using this tool, they captured an image of the supermassive black hole in the galaxy M87. It was a technological tour de force. It showed us an event horizon silhouetted against the light emitted by surrounding material and bent into a ring-shaped arc. The details of that arc held all kinds of information about the black hole. allowing astronomers to test general relativity in new and exciting ways. The black hole at the center of Messier 87 lies at the more massive end of the supermassive scale, cramming a mass that's 6 billion times that of the Sun, 6 billion solar masses, into an area the size of Neptune's orbit. But as huge as this might sound, especially when compared to the black hole at the center of the Milky Way, which is a mere 4 million solar masses, it's by no means the most massive black hole that we know of. That title goes to TON 618, which is an astonishing 66 billion solar masses. It's so big that astronomers had to invent a new term to describe it. Hence, TON 618 is what's become known as an ultramassive black hole. To give you an idea of just how mind-bogglingly big TON 618 is, imagine taking all the stars in the Milky Way and squishing the matter in them down to create a black hole. Even if you did that, it would still be a few billion suns worth of matter shy. So, how did TON 618 become such a behemoth? Black holes are made of vast amounts of matter that have accumulated in one spot and been packed together as densely as possible, to the point where the gravitational pull from the accumulation is so strong that not even light can escape it. But that doesn't mean that a black hole is a giant monster with an insatiable appetite, roaming the universe and devouring everything it encounters. TON 618, the most massive black hole we know of, still has an entire galaxy of stars happily orbiting it and not getting sucked in. It's a common misconception that black holes act like vacuum cleaners, when in reality it's incredibly difficult to grow a black hole. For a start, you have to get material close enough for it to be affected by the black hole's gravity. And when you consider how dense black holes are, due to all that matter being squashed into such a tiny space, and how vast the universe really is, you start to realize just how difficult that can be. If matter does stray too close, however, it will get pulled in by the black hole's gravity, and that gravity increases dramatically the closer you get. Think of it like walking up a hill, but the hill becomes steeper with every step you take. It's brutal. The gravity around a black hole increases so quickly that if you were to approach one with your feet first, the pull of gravity at your feet would be so much stronger than at your head that you get stretched out like spaghetti. In perhaps the best example of jargon the science world has to offer, the process is legitimately referred to as spaghettification. We see this happening to stars and clouds of gas as they get close to a black hole. Once spaghettified, the matter then gets pulled into orbit around the black hole and flattened out into a swirling disk of material. The process is similar to the way you create a pizza base by tossing the dough above your head. As it spins, the dough gradually flattens out. Once it's in that spinning disk, the matter, usually hydrogen gas as this is the most common element in the universe, will settle into a nice, happy orbit around the black hole, far away from the point of no return, the event horizon. The event horizon is the sphere around the black hole that we use to ascertain its size. The larger the event horizon, the more massive the black hole. While the matter inside the event horizon is being crushed down into an infinitesimally small space, known as the singularity, the size of a black hole is taken to be the region of space from which we no longer receive any light. It's the distance away from the singularity where you'd have to be traveling faster than the speed of light to escape the black hole's gravity. If you cross the event horizon, you're done for, officially part of the black hole and contributing to its total mass forevermore. But getting matter to cross the event horizon is what's so difficult about growing black holes. How do you move material out of a happy, stable orbit around the black hole and get it to fall in, helping the black hole swell to massive proportions? The Sun and Earth provide a good demonstration of the difficulty. Earth is in a stable orbit around the Sun, and despite the star's huge size and far greater gravity compared to our planet, it's thankfully unable to pull us in towards it. That raises a question: what actually falls into a black hole? The reason material is able to cross the event horizon is collisions between particles in the disk of material orbiting it. Atoms of hydrogen gas collide and transfer energy, just like balls on a snooker table. If you're a talented snooker player, you might be able to hit the cue ball against a colored ball and get the cue ball to stop dead, which shoots off across the table. A similar exchange in energy can happen to colliding particles in the disk of material orbiting a black hole. The particle that gains all the energy will get a boost, pushing it further away from the black hole. But the particle that loses its energy will have nothing to resist the gravity pulling on it, and gradually slide down to cross the event horizon and become part of the black hole. Not every collision will result in such a drastic energy exchange. On average, there'll be an equaling out of the energy, but eventually, one particle will have enough collisions and be unlucky enough to lose energy in every one, bringing it even closer to the black hole. It's only when the particle has a collision in the region known as the innermost stable circular orbit, ISCO, that it will finally cross the event horizon to become a part of the black hole. The ISCO doesn't exist in Newton's theory of gravity, which we all learn at school. Newton's theory says that all perfectly circular orbits, no matter their distance, are very stable. That means if an object on a circular orbit is unsettled slightly, it'll remain largely on the same orbital path. For instance, if something was somehow orbiting near the Sun in a perfect circle and was nudged by another object, its orbit might become more oval, but it would continue orbiting the Sun. That's not the case in Einstein's theory of relativity, however. As you get closer to an object like a black hole, there comes a point where, if you nudge an object on a circular orbit, or, say, one particle were to collide with another, that object couldn't correct its path and would end up spiraling in towards the black hole. That point is the ISCO. It lies around 3 times further out than the event horizon and, usually, marks the inner edge of the orbiting disk of matter. This process of particles colliding, exchanging energy and falling over the event horizon, accretion, takes a very long time. We're talking millions of years just to get a black hole to a size where it can snack on a passing gas cloud that drifts too close. Complicating matters even further is the fact that there's also a limit to how much matter a black hole can accrete at a given time. The universe effectively puts a black hole on a diet if it becomes too gluttonous. This happens because the disk of matter orbiting a black hole is moving and colliding at such an incredible speed that it starts to heat up due to friction. It's heated to such an extreme temperature that it glows like metal in a forge. The good news about this glow is that it allows us to spot black holes and measure how massive they are. The light can, and does, outshine entire galaxies, making them look like single pinpricks of light. These pinpricks were originally dubbed quasars, a portmanteau of quasi-stellar, because they look like stars but aren't stars. It was only after the Hubble Space Telescope launched in the early 1990s that astronomers could make out the galaxy of stars that went with each quasar, and their true role in growing supermassive black holes was revealed. The bad news for black holes is that the glow is so intense that it exerts a pressure outwards, radiation pressure, that prevents any more matter from falling in. If there's too much material in the disk, the radiation pressure increases and pushes material away from the black hole. There's a fine balance between the size of the black hole and the quantity of matter in its disk, and when a certain threshold is reached, depending on how massive the black hole is, the rate at which it can accrete material is capped. So, how big can black holes get? What makes TON 618 so exceptional is the sheer amount of physics standing in the way of a black hole growing to that size. But while we've known for a long time that radiation pressure places a limit on how fast a black hole can grow, known as the Eddington limit, after astronomer Sir Arthur Eddington, what we didn't know until recently was whether there's a limit to how massive a black hole can become. As far as we know, there isn't. Theoretically, you could keep on merging black holes to your heart's content, gradually increasing the overall size, as if you were making a giant snowball. But there is a limit to how big black holes can grow via accretion. In 2015, Professor Andrew King at the University of Leicester published a paper that pointed out a quirk of gravity around black holes. The quirk allowed him to estimate the maximum mass a black hole could achieve via accretion, 50 billion solar masses, but it could be 270 billion solar masses if the black hole was spinning fast in the same direction as its galaxy. At the root of this quirk is the position of the ISCO, which, like the event horizon, is related to how massive the black hole is. As the black hole's mass increases, the ISCO gets pushed further out. The problem for a growing black hole is when the ISCO is pushed beyond what's known as the self-gravitational radius. The distance that the self-gravitational radius sits around a black hole is another factor that's related to the mass of the black hole, but it also depends on the object that's approaching it. The self-gravitational radius marks the point at which the pull of gravity holding the approaching object together. Self-gravity is stronger than the pull from the black hole. The self-gravitational radius is why we're all here. It's why we're able to have entire galaxies surrounding supermassive black holes. Beyond this radius, gas in a galaxy is attracted more to itself than to the black hole lying at its center. If this wasn't the case, gas would never collapse to form stars, and instead our atoms would just be part of one giant disk of material orbiting a supermassive black hole. It was King who pointed out that when a black hole reaches 50 billion solar masses, the ISCO gets pushed beyond the self-gravitational radius. What that means is that, no matter how many collisions they have, Any particles in the disk of material orbiting the black hole will never lose enough energy to reduce their orbit to a point that allows them to reach the ISCO and spiral into the black hole. Instead, the pull of gravity from all the other particles in the disk will always be stronger than the pull from the black hole. That's if there even is a disk of material around the black hole, because any matter that isn't on a direct bullseye trajectory with a singularity as it approaches won't get pulled into a disk. Instead, it will loop around the black hole, spaghettified, but otherwise unscathed. This lack of a disk means that we won't be able to spot such a black hole, as there will be no luminous matter around it lighting up like a Christmas tree. This is why TON 618 is so interesting to astronomers. With an ultramassive black hole of 66 billion solar masses, it lies above King's estimate of the maximum limit, 50 billion solar masses, for a non-spinning black hole. Most black holes are spinning, which increases the mass they can reach before they push the ISCO beyond the self-gravitational radius, but it still means that TON 618 could be nearing its maximum possible mass. It's fascinating to consider the implications of all this. We could be approaching the point in the universe's history in which black holes start reaching their limit. If black holes stop accreting and growing in this way, then they'll also stop glowing. Quasars will begin to wink out as black holes age past their glory days. It's possible that there are other black holes in the universe that have already reached ultramassive proportions. We can try hunting for them, but without the glow of a disk orbiting around them, we'll never spot them. There could even be ultramassive black holes hiding right under our noses.
You've heard of black holes, but have you ever heard of white holes? Black holes, evil twins? They are known as theoretical cosmic regions that function in the opposite way to black holes. Just as nothing can escape a black hole, nothing can enter a white hole. White holes were long thought to be a figment of general relativity, born from the same equations as their collapsed star brethren, black holes. More recently, however, some theorists have been asking whether these twin vortices of space-time may be two sides of the same coin. To a spaceship crew watching from afar, a white hole looks exactly like a black hole. It has mass. It might spin. A ring of dust and gas could gather around the event horizon, the bubble boundary separating the object from the rest of the universe. But if they kept watching, the crew might witness an event impossible for a black hole: a belch. Theoretical physicist Carlo Rovelli said, "It's only in the moment when things come out that you can say, 'Ah, this is a white hole.'" Physicists describe a white hole as a black hole's time reversal, a video of a black hole played backward, much as a bouncing ball is the time reversal of a falling ball. While a black hole's event horizon is a sphere of no return, a white hole's event horizon is a boundary of no admission. Space-time's most exclusive club. No spacecraft will ever reach the region's edge. Objects inside a white hole can leave and interact with the outside world, but since nothing can get in, the interior is cut off from the universe's past. No outside event will ever affect the inside. Somehow, it's more disturbing to have a singularity in the past that can affect everything in the outside world, said James Bardeen, a black hole pioneer and professor emeritus at the University of Washington. For a while, white holes seemed to share the fate of wormholes, mathematically permissible contortions of space-time likely prohibited by reality. But in recent years, some physicists have brought white holes back in an attempt to save their darker siblings from an unseemly death. Ever since Stephen Hawking realized in the 1970s that black holes leak energy, physicists have debated how the entities could possibly shrivel up and die. If a black hole evaporates away, many ask, what happens to the internal record of everything it swallowed? General relativity won't let the information out, and quantum mechanics forbids its deletion. How does a black hole die? We don't know. How is a white hole born? Maybe a white hole is the death of a black hole. The two questions join nicely, but you have to violate the general relativity equations in the passage from one to the other.
That's all the information that we have for you today. Don't forget to give us a thumbs up if you've enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.